This is a tutorial video of the work IGG, Image Generation Informed by Geodesic Dynamics in Deformation Spaces, which got an oral presentation at IPME 2025. As we all know, generative models have gained increasing attention in medical imaging domain. For example, people develop generative model for brain reconstruction, lung imaging, and many other applications. People also use generative model to study multimodality imaging for disease diagnosis and treatment. Even generative model itself thinks they are very useful in various areas of medical imaging, including lung imaging, brain, retina, and abdominal imaging. However, we identified there are limitations of current generative models. First of all, they do not consider topology. For example, if we give an image to a generative model with text instructions, in this case, we ask the question, image of a 17-year-old male who is cognitively normal, how will it be at the age of 77 years? The current fine-tuned generative model on the brain dataset can generate samples that, at first glance, look quite legit. However, if you look at closely, which highlighted with the red box and arrow, you will notice that the topology is not well preserved. Let's look at the ground truth image at the age 77 for comparison. You can see how the anatomical structures have been broken. In addition, the current generative model mainly manipulates image intensity, but it does not offer a good evaluation metric to quantify the topology. Most models today rely on quantitative results, which means that you visualize it and see whether the quantity is good or the closeness to the real dataset, without a clear quantitative measures for the topology accuracy. Another limitation is that the generative model functions as a black box to the deformation process in object changes. The entire process of transforming the input image to the generated output is not exposed to the network. The generative model is completely blind to the changing process of the input image. In this work, we are interested in solving all those limitations. Our approach is especially to develop a novel image generation model that integrates geometric principles through the geodesic learning of image deformations with a powerful conditional diffusion process. Most importantly, we want to enable the quantitative metrics to assess the topology consistency of the generated samples. In this way, we can produce anatomically intact and more realistic image samples. Before I introduce our model, I would like to first review the basic concepts of geodesics in deformation spaces to make sure everybody is on the same page. So, in our context, we consider the deformation as a diffeomorphism, which is bijective, smooth, invertible smooth mapping between objects. Our work is built on LDDM, which defines a distance metric between two diffeomorphic deformations. Specifically, we are interested in the distance between the identity mapping and the deformed mapping. If we minimize the distance, we can get a locally shortest path, which is the geodesic. The geodesic is uniquely determined by the geodesic shooting equation, also known as the epidiff equation. For the epidiff equation, given any initial velocity, it generates a time-dependent velocities along the geodesic path. The velocities are then integrated to obtain the full geodesic flow of diffeomorphic deformations. Here, you don't need to worry about the mathematical notations except for the key operator, which imposes smoothness by acting as the inverse of the Laplacian. Now, We have learned how to formulate a geodesic. The next step is to derive the geodesic deformation in the image space. This is what was done through optimizing an allergy function with two terms. The first term is the data matching term, which aligns the source image with the target through the deformation phi. The second term is the regularization term, which can either enforce the geodesic shooting constraint through the epidepth equation or can be replaced by the alternative parameterizations like stationary velocity fields, which are also commonly used. We especially choose the epidepth constraint because it yields smooth, time-continuous deformations that capture the gradually changing process of the objects. So, this brings us to our model. In contrast to the previous generative diffusion models, which operates in the image space, our approach performs diffusion in the deformation space. To be more specific, in the space of geodesic flows parameterized by the velocities. This is the overview of our model IGG. Given a pair of source and fixed image, we first use an encoder to extract the no-dimensional latent representation of the geodesic. Then, a standard latent diffusion model is applied to learn the distribution of these latent geodesics. Once it's trained, we can randomly sample a point from latent distribution and project it back to a geodesic flow or deformations in the image space. Finally, we deform the source image along the flow to generate a sequence of time-continuous deformed images. However, the first question here is, how do we obtain those no-dimensional latent representations of the geodesic, which will serve as our training dataset? Which I mean, we are aiming to learn the distributions for them. We are essentially using an autoencoder-based registry model to learn the latent representations in the deformation space. In a typical way, we use a registry model. Here, the encoder compresses the input image into the latent velocity space, and the decoder projects this back to the image space to generate the deformations, which are then applied to the source image. The loss function includes two terms. A data matching term that minimizes the distance between the different source image and the fixed image. And the regularization term enforces smoothness on the deformations. In contrast to a previous approach, which only learns an initial velocity, our model learns the entire geodesic trajectory. To do this, we design a neural operator in the latent space to encode the full geodesic, which propagates from ZV0 to ZV1. The decoder projects this latent representation back into the four-dimensional space. The training process is guided through the mean-square error between the projected geodesics and the numerical solution from the neural-epidepth equation, which is highlighted in red, V hat, which is representing V hat 0 to V hat 1. They are the numerical solution to epidepth equation. Now let's take a look at the latent neural operator G theta. I used the architecture from my previous work, NeuroPDIF in IPME 2023. The key distinction is that NeuroPDIF designs the neural operator in image space. However, the current model G theta is operating in the latent space. Let's take a quick look at the architecture of it. The encoder P lifts the latent features to a higher channel space, and the decoder Q will project it back to the original channel space. The encoded features go through the compilation of the local linear transformation W plus the global convolutional curl H. The entire latent geodesic from ZV0 to ZV1 is propagated in an iterative way And at each iterative step, g theta updates the current state ZVT to the next state ZVT plus 1. The whole architecture of learning the latent representations of geodesics is pre-trained through the joint loss function. Once trained, the model can derive numerous time series of latent representations from any given image pairs. This prepares the training dataset for the diffusion process in the latent geodesic space. And now let's move on to the latent geodesic diffusion model. So, we stack the time series of latent geodesic representations along an additional channel, denoted as Z0. Keep in mind that Z0 is a time sequence along the geodesic step T. Then we perform the forward diffusion process by gradually adding noise in this space. Each step sampling is using the Markov chain parameterized by the conditional probability Q of z tau conditioned by z tau minus 1. This can be simplified by the conditional probability of z tau conditioned on the initial latent feature z0. So we can compute z tau directly from z0 through this equation. The reverse process is gradually removing the noise from the previous step. So the current sampling is parameterized by the conditional probability, P of z tau minus 1. Similar to the standard DDPM diffusion model, this entire reverse diffusion is basically implemented through an ULAT architecture. But the difference is that the conditional probability not only conditioned on the previous step, it's also conditioned on the gradient of the input image and the text. The reason why we use the gradient of the input image as the condition is that, according to the LDDM plus the geodesic shooting, the optimal solution of that is defined on the gradient of the image. The network is trained using the MSE error between the predicted noise and the ground truth noise added at each diffusion step. Let's move on to the experimental results. We conducted experiments on two datasets, Kamasulla plant dataset and Awitha 3 longitudinal brain MRI that capture the deformable shape changes over time. We first evaluate the model's ability to capture geodesic dynamics by comparing the learned geodesics with the numerical solutions to an EPDF equation. In the left panel, the predicted transformations, velocities, and the deformed images from IGG's autoencoder closely resemble those obtained from solving EPDF. The right panel shows the mean square error between the numerical solutions and IGG's predictions at each time step, with consistently low error indicating IGG's effectiveness in nearly accurate geodesic mapping. For the diffusion results, let's take a look at an interactive application of our model. By uploading a template image and provides an editing text, our model generates a target image along with the intermediate transformation process. We also evaluate the fidelity and the topology of the generative samples, compared with the three state-of-art video diffusion models, which diffuse the shape changes over time in image intensity space. Given a plant at 200 hours, we predict its appearance at 208 hours. IGG clearly preserves object's topology and captures the gradually geometric changes over time. In contrast, the baseline often produces unrealistic hallucinations that break the topology structure. For example, the yellow box highlights the topology violations. The second baseline, called video X, frequently generates distorted colors that don't align with the input. While some samples look plausible, hallucinations occur frequently. The same story for brain datasets. Our model IGG is the only model that preserves the topology structure and captures the gradual geometric changes over time. We further compute the determinant of Jacobian values for the deformations generated by IGG, which is not available for the baseline since they don't output the deformations. We can see what the determinant of Jacobian values are above zero, indicating no topology breakage and confirming IGG's ability to maintain the anatomical integrity. We also use the regular metric that people always use for the generative models. We can see IGG achieves the best performance. Finally, we evaluate the diversity of IGG by computing the pixel-wise standard deviation of 1,000 generative samples. Given the same input template and the text instruction, we compute the diversity for the generative samples on the geodesic paths, which are shown as the emissions, which for brain is reflecting the expanding patterns in the ventricles and for the plant capturing the growth pattern of the plants over time, primarily focusing on the boundaries of the leaves. The final takeaway of this work is we introduce a novel image generation framework that deforms the template along the generated geodesic pathways in the deformation spaces, guided by text. It provides interpretable transformations and quantitative metrics to assess the topological consistency in the generative images. Our future work will leverage IGG's output to benefit downstream tasks, such as image classification, segmentation, and object regulation in medical domain. If you are interested in more details, you can dive into the paper and code through the QR code. Thanks for your attention.